Hey, mathletes. What we're going to look at in this video is a rather important little tidbit in calculus called the first derivative test. So remember what we've been doing is we've been practicing slowly getting towards graphing functions algebraically without a graphing calculator. So we continue on that little journey today by learning the first derivative test, which might sound scary, but it's not. It's actually pretty easy to do. Okay, so again, let's go back to a visual first. So consider the function f at x here, which has a critical number at 2. And again, I know that's the critical number because the tangent line has a horizontal slope. So how is the derivative behaving before and after x equals 2? Well, to the left, the derivative, remember the slopes of the tangent lines would be positive. So to the left are positive. At our critical number, the slope of our tangent line is 0. And to the right, when we're getting larger, our tangent lines are negative. So what we just had here was we have a maximum when we went from positive, slopes of our tangent lines went from positive to 0 to negative when the slopes of our tangent lines went to negative. Okay, so what you're seeing here is a really easy way for us to tell if we have a relative max or min. Now, let's just investigate one more case. Look at this function, x minus 2 cubed. So what's happening now around this critical number of 2? Well, I can tell visually right now that unfortunately that's neither a max nor a min. But algebraically, what we're going to find out is that the slopes of the tangent lines to the left are positive. The slopes of the tangent lines to the right are positive, and the slopes of the tangent lines at that moment are 0. So just because we have a critical number, we don't end up always with a max or a min. So our slopes of our tangent lines went from positive to 0, but back to positive. So remember what Fermat's theorem tells us. It tells us if we have a relative max or a min, it must occur at a critical number. But the converse isn't true, that just because we have a critical number, it does not guarantee we have a relative max or min. Okay, so just one thing to keep in mind, just because you found a critical number doesn't mean you have a max or a min guarantee. So here we go, the first derivative test. So for a critical number c in between a and b, c is a critical value, then f at c is a local max if the slopes of our tangent lines go from increasing, positive, and down to negative. So we can think of that as going from positive to negative. Our function at c is a local minimum if we go from decreasing, so when our derivatives are less than 0, to increasing when our derivatives are greater than 0. So you can think of that as going from negative to positive. There is no max or min if the derivative does not change signs before and after a critical point. Okay, and that'll happen. So just one thing to watch out for, just warning you now. Okay, let's go and see how the first derivative test works algebraically. Okay, so we got to take the derivative of this thing. So I'm thinking product rule. So the derivative is f prime at x first times the derivative of the second, which is 2x minus 2, plus the second times the derivative of the first, right? Okay, let's just do some simplifying here. So it's looking a little ugly. So first what I'm going to do is I'm just going to rewrite the first term like that. And then the second term, I'm just going to bring that 3x squared like that. Okay, now what I'm going to do is I'm going to factor this thing. I like things factored. So I'm going to factor out an x squared and an x minus 2. What does that leave me with? Well, it leaves me with 2x plus 3 multiplied by x minus 2. And now what I'm going to do is I'm just going to simplify inside my brackets there. So x squared, x minus 2. And what do we end up with here inside our brackets? 2x plus 3x sounds like 5x minus 6. Okay, so we do all that good work. We take the derivative. Okay, so now what we're going to do is we're going to find our critical numbers. So remember, our critical numbers are where the derivative is equal to 0 or does not exist. Again, this is a polynomial, so it exists everywhere. So I'm only going to check where the derivative is equal to 0. Okay. So I set my derivative equal to 0, and this is why I factored it, friends. Because now, watch how easy this is to solve. X is equal to 0, x is equal to 2, x is equal to 6 over 5. Okay, there's my critical numbers. Now I'm just going to go back. Our domain that we wanted to look at was from -1 to 3. So what we're going to do then is we're going to go and we can do our sign analysis chart. So our sign analysis chart, I'm going to put down my critical numbers. Remember, we're stopping at -1 and we're going to 3. And our critical numbers go 0, 6 over 5, and 2. And what I'll do here is I'll pick a number on each of these intervals. So maybe -0.5, 1, 1.5, and 2.5. Okay, so now what we're going to do is we're going to sub these values back into our derivative and see what we end up with. Okay, so I sub in -0.5. Remember, I don't care about the value. I only care about the sign at the end. Okay, so I sub in 0.5. Well, -0.5. The first term is always going to be positive. So I don't even have to worry about that first x squared. So -0.5, I'll get a negative right there. And then I'll get a negative in the second bracket. So that's going to end up being a positive value. Then I'm going to sub in 1. So again, 1 squared, 1 minus 2, that's a negative. And then on the last bracket, 5 minus 6, well, that would be negative. So I'm going to get a negative times a negative, which is a positive again. Then I'm going to sub in 1.5. So I'm going to get 1.5 minus 2, that's a negative. And then in my last bracket, I would get 7.5 minus 6, that would be a positive. So a negative times a positive is a negative. And then if I sub in 2.5, I'm going to get a positive and a positive. That'll be a positive. Okay, so what's happening here? Well, right here, when x is 2, we went from a negative to a positive. That means we went from decreasing to increasing. That tells me we have a relative minimum here. Now, it might be an absolute minimum, but I don't quite know yet. For sure, it's a relative minimum. So I have a relative minimum when x is 2. What I can do from here is I could go back and find what that y value is. So to find that y value, I go and sub 2 back into our original function. Well, guess what? When I sub in 2, I see that it's going to be 0. So I've got a relative minimum right there on the x-axis. Okay, what's happening at 0? Or how about right here? What's happening at 6 over 5? Switch pen colors. What's happening here? Well, we went from positive to negative. That means we went from increasing to decreasing. That's a relative max. So we have a relative max when x is equal to 6 over 5. And again, that max would be at whatever value that happens to give me. Okay, well, for that one, I think I'm going to finally pull out a calculator here. And so if I stick 6 over 5 into this beast, what am I going to get? I don't know. Let's figure it out. I get approximately 1.1. Approximately. So we have a relative max at 6 over 5 and approximately 1.1. And what about at 0? Well, at 0, we went from positive to positive. That means there's no sign change. That means this is not a max or a min? It's nothing. Okay. So what does this thing possibly look like then? It's kind of funky looking. Well, look at what we can start to do again. We're not going to quite get the perfect graph, but we can start to sketch this thing. So what do we know? Well, if I even just go back to the original function, I can see I have x-intercepts at 0 and 2. So I have an x-intercept at 0. I have an x-intercept over here at 2. And now I don't quite know everything about this function, but I know I've got a relative max at 6 over 5 and 1.1. So let's label that right there. That's 6 over 5. And we'll call that 1 right there. So it's just a little above 1. And we've got a relative min, which happens to be at our 0. Okay. And so what do I know is happening? Well, for sure, I know it tells me we're increasing from -1 to 0. So here's -1. So I know we're increasing from -1 to 0. It's probably going to do something like that. Then from 0 to 6 over 5, we're still increasing. So all I know is I'm coming up to here. That's my relative max. Then I have to decrease down and I'm going to hit here. But then after it tells me I'm increasing, so what's going to happen is I'm going to have a point of tangency there, and it's going to look something like that. Okay, now what we just did was we found our relative maxes and our mins algebraically. At this point, I pick up my graphing calculator and I graph it. So let's go find out. So I grab our graphing calculator and let's go find out what we get. So what the heck was our function again? It was x cubed x minus 2 squared, wasn't it? Okay, let's hit graph. Look at that. Hey, I did a pretty good job. I'm actually going to zoom in a little closer. Our domain that they asked us to graph on was -1 to 3. Not bad. Look at that. Okay, now I'm not even doing a full analysis here yet, but I got pretty darn close, didn't I? So you can see where we're going to start taking this. We're going to keep going every lesson further and further, and we're going to practice graphing these things by hand. So there it is, friends. There's the first derivative test. Hope that helped. I will see you again another time.